Classifying breast cancer cells with measurable characteristics, presented by Benjamin Stanley. Background. Every year, about 240,000 women and 2,100 men are diagnosed with breast cancer, and every year, 42,000 women and 500 men die of breast cancer, making the identification of cells that are malignant especially important, and early identification incredibly important. And anything that can be done to help speed up the process of identification can add additional valuable time to patients' lives and to allow them to receive treatment faster and potentially provide them with better outcomes. And so one way to do that would be to develop a model that can tell the difference between benign and malignant cancer cells in breast cancer. So for this presentation, I created two models, a linear regression model and a support vector machine model that I will use to compare their ability. I will use both to compare their abilities at classifying breast cancer cells as either benign or malignant based on measured physical characteristics collected at the University of Wisconsin. So models. Let's get into the models. The math behind it, linear regression. Linear regression is a fundamental statistical method used to model the relationship between one or more independent variables and a dependent variable. The aim is to find the best fitting straight line that represents this relationship. It's like drawing a straight line through a scatter plot of data points to summarize their overall trend. Now, when it comes to binary classification, linear regression can be adapted to predict the probability of an event happening, such as whether an email is spam or not, or whether a patient has a certain disease, or whether a customer will purchase a product. Here's how it works. Instead of directly predicting the outcome yes or no, linear regression predicts the probability of the outcome occurring, typically represented as a value between 0 and 1. Then we set a threshold. In this case, for this project, I chose anything above 0.5 or above as malignant, anything below 0.5 as benign. And then they are classified. For instance, let's say we're predicting whether a student will pass or fail based on their study hours. We collect data on study hours and whether each student passed or failed. Then we use linear regression to model the relationship between study hours and the probability of passing. The output of the regression equation gives us the probability of passing for any given number of study hours. However, linear regression has its limitation from binary classification because it assumes a linear relationship between the independent variable and the log odds of the dependent variable, which may or may not always hold true. It can also produce probabilities outside of the 0 to 1 range, which doesn't always make sense if the model is not set up correctly. Now onto that next model, the math behind it, support vector machine. So SVMs, or support vector machines, are a supervised learning model that's used for regression and classification tasks. The key idea behind SVMs is to find the hyperplane that best separates the data points into two different classes, while maximizing the margin, which is the distance between the hyperplane and the nearest data point from each class. So essentially, if you were able to draw, the goal is to find a line that separates the two groups as perfectly as possible, while also having as much room between the groups and the line as possible also. So imagine you have your data points plotted in a multi-dimensional space. In this case, for ours, we had 30 features, meaning it would be a 30-dimensional space. And you have to draw a straight line or a hyperplane in higher dimensions is what it's called. That best separates all the different points from all the different classes. And in this case, there's two classes, but separates all of those points in this 30-dimensional space. It's kind of hard. So in classification tasks, SVMs can handle linear separability as well as non-linearly separable data by using techniques like kernel trick, which map the data into higher dimensions, which becomes linearly separable. Now, let's move on to principal component analysis, a type of analysis performed before we use the support vector machine on our data. So PCA, or principal component analysis, is an unsupervised dimensionality reduction technique that is used to help reduce noise and allow for visualization. PCA works by reducing the complexity of the data set or the feature space down to a two-dimensional space. By reducing the and it does this by reducing all the features down as much as possible while still preserving as much original information as possible. The principal components are ordered by the amount of variance they explain, allowing you to choose a subset of components that retain most of the variance while reducing the dimensionality of the dataset. For instance, in a dataset containing information about housing prices with numerous features like square footage, number of beds, bedroom, or whatnot, PCA can be used to reduce those features into a smaller set of principal components that still captures the essential information about house pricing, while making that data easier to visualize and analyze. In summary, SVMs are a powerful tool for classification, and they allow the handling of both linear and classification of both non-linear and linear data. But PCA is a useful technique for dimensionality reduction, particularly in situations with high dimensional data, such as our case. And this can help to reduce the number of features that can lead to simpler, more useful models. Okay, so for this project, we used, as I said before, data with 30 measured characteristics of cancer cells obtained from the University of Wisconsin. And in that, the 30 different features, it's 10 features that are taken 3 different times on 3 different measured slices of the cell. So essentially, while it was being measured, it took 3 different depth slices. So there's going to be measurements of 3 different heights of the cell. And so here I plotted the correlation of each factor to the diagnosis. And obviously the diagnosis has a 1-to-1 correlation ratio with itself. And interestingly enough, the middle slice of the cell, number 2, has the lowest correlation for every factor compared to the 1 and 2, and that the 1 and the 2 are far more highly correlated. And that shows down here too in our top 5 highest correlated features, which are concave points in the 3rd slice, perimeter of the 3rd slice, concave points in the 1st slice, radius of the 3rd slice, and the perimeter of the 1st. And so to get a better idea of what the data for those most highly correlated features looks like, I did box plots separating the data by benign and malignant. And in this first one with concave points, that refers to the number of concave points on the cell in that slice. And as you can see, fewer concave points tends to mean benign, but the spread is relatively wide for both. But the majority of the data points do lie fairly separate from those of malignant. And move on to perimeter, just like, and with the perimeter, it looks like a smaller cell tends to be an indicator of benign tumors rather than malignant, and those larger tumors tend to be much more likely to be malignant. As you can see, all those higher outliers in size are all going to be malignant, while the lower end are going to be benign in terms of size. Then we got concave points in slice 1, just like we did for slice 3. But in this one, in slice 1, there are much more, a lot more concave points, or a lot fewer concave points than there were in the one before. You can see here, its 50th is right about 0.2, but in this one, the 50th is lower than 0.1. But it still shows that same trend of fewer concave points tends to point towards benign. Then we have the radius of the third slice. Once again, a smaller size tends to indicate that it is benign rather than malignant. And perimeter of 1 also follows that trend. Now, this is that support vector machine I was talking about. This is the visualization, and this is one of the benefits of performing PCA on a data set, is that it takes the high dimensionality data sets like ours, which has 30 features, and it smashes it down into a two-dimensional plot that is able to actually be, or two-dimensional data set that's actually able to be plotted. And so here you can see and actually physically view where our support vector is, and that's this line right here. This is the line that was chosen as best able to separate the benign from the malignant. You can see if we got a benign, or here we got a malignant, and the support vector flows right through. And these are the margins. These are what we were trying to maximize as much as possible. But in a case like this, it's a little harder with how much overlap there tends to be in data. Because you can see even though the line does pretty well at separating them, there are a couple of little data points that slide onto either side where they shouldn't be. But this is a visual representation of what that hyperplane is doing in feature space, except rather than being a two-dimensional line, it is a hyperplane running through 30-dimension space. Now, how did the two models do? What were the results? Linear regression had an accuracy of 0.9532, and the support vector machine had an accuracy of 0.9707. Accuracy wasn't necessarily the factor we looked immediately to in this case for determining which model was better. In this case, due to the fact that it was a medical scenario with diagnoses, recall is an important factor, an important metric in medical cases, because recall essentially how right the model gets that individual case. So like in this case, we have a recall of 0.88 for 1, which is a malignant a cell classified as malignant. So that means that 0.88 or 0.88, not percent, 88% of the time, the model was able to correctly identify a malignant tumor as malignant. And recall, also known as the true positive rate, is calculated by number of true positives. So in this case, it's ones that are 1 in the data set, or the diagnoses that are 1 in the training set. And it's number of those correctly found over true positives plus false negatives. So the number of times that a diagnosis where it was 1 was identified as a 0 as benign rather than what it actually was, malignant. So the recall rate is important because it's in medical situations such as a diagnosis for cancer or other diseases, you would much rather diagnose someone with it and have it be a false positive than be a false negative. Because if someone is incorrectly told they have a disease, you will find that out through further testing or when treatment doesn't do anything because you don't have the disease. But if you receive a false negative, you don't have that chance to receive your treatment and you lose out on time that could potentially be important in saving lives. And so you want to err on the side of caution, and you want to, as frequently as possible, make sure that you are correctly identifying those malignant cases when they are there. even over accidentally giving someone a scare that they have a malignant tumor when it's just benign. So when comparing the results, despite the fact that precision was higher, was higher in the malignant case, the recall was significantly lower than the recall on the support vector machine. So we have to go with this. I have to go with the support vector machine as the more competent model for classifying benign and malignant tumors. Thank you for your time.